introduction to 4.5 on the chain rule and 4.6 on combining the rules. I just asked you to complete question 8a as a do now question. Let's go through it very quickly. Of course, because they're multiplying, I'm going to be applying the product rule, which means I'll just quickly scroll back up, this rule right here. We're going to differentiate one of the functions or one of the sections of it and multiply it by the other section that's not differentiated. And again, because it's addition, it doesn't matter what order. So you should end up with, and you may have it in a different order. Oops. I'm going to say sorry. I'm going to zoom in a bit. There we go. Let this equal to f of x, and then f dash of x equals to, there we go, equals to, I'm going to differentiate the first one, which of course gives me 4x, and I'm going to multiply that by the remainder, which is 5x cubed plus 16, and I'm going to add the original function, 2x squared plus 1, and multiply that by the differentiated of the second one, which is 5x squared. I'm getting some confused faces. What's going on? No?
I thought you were supposed to expand the bracket and then...
You can expand it, but we can apply product rule. So if you expand it, you can fully expand it and then differentiate it. You'll get the same answer. It just, in some cases, it will take more time to do that. In this case, I'd say maybe about the same time. But if I simplify that, that'll give me 4x bracket 5x cubed plus 16 plus, and I'm just going to write 15x squared bracket 2x squared plus 1. And that will suffice as a differentiated function. What you might like to do is, in an exam, as I was saying earlier, just leave it in this form. And then if you need to substitute x equals to whatever it is to find a differentiated equation, or differentiated value, sorry, that is fine. That will suffice. Great. Are we happy to move on to today's content? Okay. Chain rule. Chain rule is a little bit more complex. It's not just a rule, but it's a general process. If h of x equals to g of f of x, then the derivative of h of x, or h dash of x, equals to g dash of f of x times by f dash of x. I will explain what that means. But the rule I want you to focus on is actually this one right here. dy dx equals to dy du times du dx. It's very important that we know this one. For me, this one is a lot easier to interpret than the first one I said. But I think it's fair to say that we know these are the same. Because of course, if we just cross simplify, you just end up with dy dx, right? Agreed? Good. What we're going to do is we're going to define a section or a smaller component of our function as u. And that makes things a lot easier. Conventionally we use u, there's nothing wrong with using other letters, but we're going to use u. Let's look at example 7. Find the derivative of 10p bracket 1 minus p to the power of 9. What I'm going to do is, because this is technically a combination of the rules, I'm going to focus on just this component here. The 1 minus p to the power of 9. And I promise we'll use this, but I'm going to write, I'm going to let y equal to bracket 1 minus p to the power of 9. What I'm going to do now is, if I was to differentiate it manually, I'd have to expand it out. And to me, to the power of 9 is horrendous. Yes? Instead of doing that, we can try to use a rule that makes it a lot easier to understand. I'm going to let the inside component equal to u. Let u equal to 1 minus p. Is it now fair to say that y equals to u to the power of 9? Yeah, it is. It's fair to say that. And then we can actually just straight up apply our rule, our chain rule, to find the derivative of bracket 1 minus p to the power of 9 without expanding it completely. I'm going to skip a step up. Instead of writing dy du equals this, dy dx, etc., I'm going to jump straight to using the formula. dy dx equals, again, because we're multiplying, order doesn't matter. I'm just going to be consistent and use dy du first. So dy du is saying derive the function of y in terms of u. Just like normally it's dy dx, derive function of y in terms of x. We're deriving y in terms of u for our first component there. Right now we have y equals to u to the power of 9. So if I derive that in terms of u, it'll be 9u to the power of 8. Hopefully that seems very accessible. I then multiply that by du dx. So now instead of saying, I realize now it should have been p, my apologies. This is dy dp because the original function is y in terms of p. In this case, instead of using x, we're just using p. So now to find du dp, it's derive the function of u in terms of p, correct? So the derivative of the function of u in terms of p, which is just going to be -1. Because I'm deriving 1 minus p in terms of p, of course, 1 becomes nothing, negative p becomes -1. So the derivative of bracket 1 minus p to the power of 9 is going to equal to -9u to the power of 8. But there is an issue. There's a slight issue. And the issue is we have defined u ourselves, not the question. What we need to do is put it back in. We know that u equals 1 minus p. I'm just going to write equals to -9 bracket 1 minus p to the power of 8. I'm just substituting it back in. Any questions about that? Okay. At this stage, use the let equal u, right? Even I, right? If it gets to a very complex question, I'll let a component of it equal to u and work through it there, especially when we're deriving, for example, our trigonometric functions or our e of x, logs, etc. You'll get to a point where you can just look at it and know how to do that chain rule without substituting for u, right? You don't have to substitute for u. That is just an option. That just makes it a lot easier to understand. Now, if we go back to our original question, and we're going to combine the rules now. Back to our original question, we have 10p multiplied by 1 minus p to the power of 9. Of course, multiply, if I want to find the derivative of the whole thing, I would use the product rule. So I'm going to write out d over dp. So I'm deriving insert function in terms of p of 10p bracket 1 minus p to the power of 9. Are we all okay with this notation? You'll see this come up quite often. The derivative of bracket over dp, so the deriving this function in terms of p, equals to, and using product rule, I'm going to derive the first one, so that becomes 10, multiplied by 1 minus p over to the power of 9, sorry. So I'm just going to derive 10p and leave the second component as it is. And then I'm going to add the original of the first component, so 10p, multiplied by the derivative of the second component. We've already done that. We said it was -9 bracket 1 minus p to the power of 8. So I'm going to multiply that -9 bracket 1 minus p to the power of 8. Because this is now a reasonable simplification, I should be expected to just go 10 bracket 1 minus p to the power of 9 minus 90p bracket 1 minus p to the power of 8. That is a reasonable simplification, and so you should be expected to do something like that. That is a combination of both the product rule and the chain rule. It looks very complex right now, but again, we're going to focus on the chain rule, and once you're familiar with that, it'll be a lot easier to apply. After that, we're going to jump to question 8b, example 8b. I'm going to leave that on the screen for a second. Here we go. It says x cubed, bracket 3x minus 5 to the power of 4. Again, which rules should I be applying? Product, quotient, chain. Which one should I be applying? And chain. Good, because I've got something to the power of something as one of the components. So same thing. I'm going to do it I'm going to skip a couple of steps this time. I'm going to show you what it looks like when I don't use sub u, okay? So, I'm going to, again, write d over dx. This time it is dx because it's in terms of x cubed, 3x minus 5 to the power 4. I'm just writing the derivative of this function. Equals, I'm going to write down here because I think I'm going to run out of space. So it's product rule. So I'm going to keep the first, actually, let's make it easier. I'm going to derive the first one and then keep the second one. 3x squared multiplied by 3x minus 5 to the power 4. So I've derived the x cubed and left the 3x minus 5 to the power 4. Of course, that's not our answer because product rule tells us that we need to add, and then we do the opposite. So I'm going to now keep the x cubed. I'm going to multiply by the derivative of 3x minus 5 to the power 4. If you'd like to do it to the side, you can do that absolutely. I'm going to do that right now. So I'm going to take this component right here and figure out what the derivative of dx, so derivative of 3x minus 5 to the power 4 is in terms of x. So instead of using the substitute u, which you absolutely can, I'm going to skip that step. I'm going to derive, and remember, pretend the 3x minus 5 is one variable. I'd bring the power to the coefficient. I get 4 brackets. And instead of writing u, I'm just going to write the original function, 3x minus 5, to the power of 3. And remember, I multiply by the derived inner component. So multiply by 3. Because 3x minus 5 derived is 3. Any questions? Okay. Are we starting to wrap our mind around this? Yeah. And then I can just bring that back into my larger function. Because remember, we're multiplying by the derivative. I'm going to write that in here. 4 bracket 3x minus 5 to the power of, what did I say it was? 3? Yep. Times 3. Again, that is a reasonable simplification, which equals to 3x squared bracket 3x minus 5 to the power of 4 plus 12x cubed bracket 3x minus 5 to the power of 3. Have I gone through that too quickly? Up the back, can I have a nod? Or not a nod? Thank you. Let's go through another example. This one here, there we go. X minus 2 over x squared plus 4x plus 1. What differentiation technique should I be using? Sorry? Quotient. Do I need to use another rule? Not really. I mean, the bottom is very easily differentiated. If you really wanted to make your life difficult, what you could do is say that this is equal to x minus 2 multiplied by x squared plus 4x plus 1 to the power of negative 1. Would you agree they're the same thing? If you wanted to, you can then apply your product rule and your chain rule to do that. It makes your life so much more difficult. I don't know why you do that, but it is a possibility if you forget your quotient rule, for example. Yeah? Okay, we're not going to do that because that is a waste of time. Instead, let's just apply our quotient rule. I'm going to be a bit lazy and just write d bracket dx in front of that. And I'm going to apply my quotient rule. So quotient, remember the order does matter. That equals to, we're going to derive the top function, so that's just going to be 1. And I multiply that by the bottom function, so x squared plus 4x plus 1. And then I'm going to subtract the original top function, multiply the derivative of the bottom one. Sounds familiar? Okay. And then of course divide that all by the square of the bottom, which is x squared plus 4x plus 1 all squared. Okay, any questions? No? Simplifying that down, it's just going to be x squared plus 4x plus 1, minus, and I'm just going to do that expansion now because I know that I'll be able to simplify the top terms. So that becomes bracket m, use the big bracket, so I'm just going to multiply those together, get 2x squared plus 4x minus 4x, and then minus 8, all divided by x squared plus 4x plus 1 squared. And then I'm just going to simplify that. It becomes x squared minus 2x squared negative x squared. Those two cancel out, so I just end up with plus 4x, and then 1 plus 8 gives me plus 9, all over x squared plus 4x plus 1 all squared denominator. And that will suffice. If you're feeling pretty confident, you feel like you're okay, I'd like you to get started on the exercise 4.5, 4.6 questions. I'm going to go through one more example of chain rule, because I feel like that's the one that's quite tricky. If you're following along with me, can I get you to write down the following example? We're going to ignore question D. I'm going to write E and write, let's say, y equals to 6 x squared minus 3x to the power of 17. Okay, so first thing, step by step, I'm going to define the inner function as u. So let u equal to x squared minus 3x. And I can rewrite that as y equals to 6 u to the power of 17. Any questions, qualms, or queries? Okay. What I'd like to do now is just off to the side, let's just find dy du. I feel like that's super easy, right? So let's go dy du, because I know that's going to be part of my equation later. There we go, dy du. So I'm deriving the equation of y in terms of u. So 6 times u to the power 17 then becomes 6 times 17, which off the top of my head is 102. 102. U to the power of 16. Great, and then underneath that I can write du dx, which is the derivative of the function of u in terms of x, which is going to be 2x minus 3. Okay? Well, let's apply a formula. Our formula is dy dx. You don't have to write this part, I'm just rewriting it. Dy du times by du dx. And then we can then substitute our variables. So dy du we've said is, according to our function from above, is this one right here, 102. 102 u to the power 16. Multiply that by the du dx, which we said is 2x minus 3. Don't forget your brackets. We're not done yet. Why are we not done yet? We introduced u, didn't we? The question didn't introduce u. So we need to then redefine u. We know what u is. Let's put it back into the equation. So that equals to 102 bracket x squared minus 3x, because that's what we said u was, to the power 16, multiply that by 2x minus 3. Ignore the 5, it's just the page number. And that'll suffice. If you want to, as an optional, you can write 102 bracket 2x minus 3 bracket x squared minus 3x to the power 16. that's purely optional. It's fine. They're both the same thing. And that is the differentiated version of our equation of y without fully expanding to the power of 17. Any questions? Okay.